Okay, first of all, I'm thankful for whoever built this podium because my previous talks, the podium was here, and then I'm like standing like this. So, great start. So yeah, going so well. So hello everyone, my name is Pradnya, and I'm going to talk about some SwiftUI optimizations today. All right, let's get started. I don't believe in any agendas, aka spoilers, so just jumping right in. And yeah, so this is a SwiftUI view, pretty. And when we look at this view, what would we think? And when I told you it's a SwiftUI view, you would think, oh, how was it built? Or maybe, how does the code even look like? Here you go, this is the code. It's a Z stack with a gradient in the background, obviously. The gradient here is in a constant state of animation, as you can see. And that gradient is overlapped by a V stack with a text and a circle, which is supposed to look like sun. I'm sure you got that. Quite simple, nothing so special about it. But have we ever asked this question? How was this view rendered on screen? How does SwiftUI code get converted into the display? Perhaps we have, perhaps we haven't. So our question for today is, how is this view or any SwiftUI view rendered on the display? And the short answer to that question is render loop. Let's try to understand what that is. And this is its technical definition. So render loop is a continuous cycle that manages how your app's UI is updated and displayed on the screen. It ensures that any changes in the app state are reflected in the user interface efficiently, right? Some keywords there that we've highlighted. Now, render loop in itself is a bit of a complex process, but to make it easier to understand any complex process, I first try to understand where we are going towards and what is the end goal look like. And that would be the display buffer. Simply put, display buffer is the representation of every single pixel on the screen. Or in other words, it's a memory area that holds pixel data for UI elements that will be drawn on the screen. When ready, it is supplied to the display for user to see. Right, so keeping that in mind, this is the diagram that represents the render loop. We will look at each phase in detail, so don't worry about all the text on the slide. But yeah, let's look at this render loop from the context of the example that we saw before. First phase is the event phase. So the render loop itself begins when an event occurs that may change the state of your application. Events like user interactions or changes in the external data, like you received some kind of network response. That's all sort of related to state changes. And outcome of this state is only the identification of those changes. So we haven't done anything yet. We are just trying to understand what if something has changed, and if it has, what is that, right? From the context of example that we saw, as I said, the gradient here animates. So this is the method that was doing that. It's kind of starting a timer, and that timer is going to sort of change a variable, which is called gradient index. And of course, this is a state variable, and that is related to the background that we just saw. And another change that simultaneously is happening, as you can see, is the change in the position of the yellow circle, which is also represented by another state variable. So in this phase, basically, we have identified two state changes, and that is the outcome of the event phase. With that in mind, the second phase is the view update phase. The main purpose of this phase is to build a view hierarchy, like a new view hierarchy from those changes, if anything has changed, in fact. So the updated states were already identified in the event phase. In this phase, we are going to look at the affected views, and then we are going to apply a diffing algorithm and compare the new view hierarchy with the previous one. And this is where SwiftUI really shines. A UI kit didn't have this, so that's why it's faster. And it's going to come up with a set of changes required to update the UI, and ensuring that only the necessary parts of the view hierarchy are marked for re-rendering. And of course, the outcome is going to be a new view hierarchy that's going to reflect the state changes that came before. Let's take these two frames, for example. The frame on the right represents the new view hierarchy, and in the ongoing animation, SwiftUI is going to identify two elements that have changed, and is going to apply the changes and come up with this new view hierarchy that you see on the right. Do know that this is a very, very simple example. In practice, you could have like a very small view, a sub-view changing, or you could have the entire thing changing. If you have like an environment variable that has changed, then probably like a lot of other things have been impacted. So this phase can be like fast or slow depending on how you design those things. Right, so the new view hierarchy that we got is going to be passed to the next stage, the render phase, which is, of course, a pretty important phase. This is where the display buffer is going to be created, and the layout calculations and the visual properties and like colors, etc., are going to be applied in this stage. And our new view hierarchy can be transferred to a format that GPU understands, which is basically what we call display buffer. And then the last phase is just displaying the buffer that was created. This phase is where GPU takes the display buffer and executes all the drawing commands. It's converting the pixel data from the display buffer into final visual output for users to see. Right, so now that we've seen all of those phases, I want to show you a slightly different representation of this render loop. Right. In this representation, you can see the render loop in action with multiple frames. So let's imagine a view that is in constant state of change. It can be an animation or a scroll, which is, of course, obviously also an animation. So something that's constantly changing, right? So let's draw our attention to this frame with a red border, frame number 4. So once some event occurs, it's going to be in the event phase. It's going to move on to view update phase, and the state changes are going to be applied, and a new view hierarchy is going to be created. Those changes are then drawn in the render phase, and finally display on the device. So yeah, in this representation, you can see multiple frames in action, and that's how it's helpful to imagine your view. Like if you have some issues in animation, like this is where you're going to go and find out where the lags are, right? And as you may have noticed, the x-axis here denotes the time. So the distance between frames is what you usually call frame rate. And frame rate can be 60 FPS or 120 FPS depending on your device. Usually ProMotion devices have a 120 frames per second frame rate, so smoother. And that basically means that the distance between the red lines is either 16.67 milliseconds or 8.33 milliseconds. And that's the time that you get to prepare the next frame in every single phase. So since it's like running from one frame to the next, like every single time, you get that much time, and yeah, that's how it works. So usually 120 frames per second, life is bright and sunny. Always, it doesn't always happen. So let's look at a scenario where you have a hitch or a lag. So as we can see here, the frame has progressed from event phase and view update phase to the render phase, but something went wrong in the render phase, and the engine took too long to create the display buffer. Too long meaning it exceeded the allocated time that we talked about earlier. And a direct consequence of this is that the frame 3, which is the previous frame, has appeared on the display for one extra cycle. This means that the transition that user was supposed to see will appear laggy, and this, my friends, is what you would call a hitch or a frame drop. And you must have seen this, I'm sure, in your own apps, in some other apps. And when we say the scroll isn't smooth enough, this is what has probably happened. One of the phases of the render loop took too long, and the next frame wasn't prepared in time. And that basically led to some kind of lag. Note that in this example, like the lag has happened in the render phase, but in practice, any phase, like if you mess up, like any of the phases could basically take too long. Right, so yeah, too much theory. And for the purpose of this talk, I decided to kind of challenge myself and build animation that was laggy. And after too many difficulties that I almost want to refuse to admit, I created this animation that was lagging. And I think surely I must be the first person to publicly brag about how laggy my animation is. But let's not fret, that was for science, so yeah. All right, so I'm going to add some context around this animation. Initially, when I created it, it was less than 10 clouds. And the clouds are, by the way, custom shapes, so they are not images. And that's how it was looking. I think it looks pretty okay. And then I decided to increase number of clouds. Say it's a particularly cloudy day. So how does that look like? It sort of looks still fine, only for 2 seconds. After 2 minutes, this is how it ends up looking like. And as you can see, it's very, very laggy. Like you can literally notice how much it's hitching. Hopefully, yes, that is visible on the screen, great. And that doesn't provide a good experience. You really want to make it feel natural and stuff like that. So yeah, and it's not just the screen lag. When I check the CPU report, after about 3 minutes of usage, I think CPU consumption is more than 100%. It is quite bad because this is basically what's going to affect your battery life. So you really want to be careful of how much battery your app consumes, and then this is pretty bad in that. So yeah, let's understand what happened and why is it laggy. I'm going to show you some code, yeah. So Skyview is the entire screen that you see. Here, the number of clouds is basically injected from the super view. So I can control how many clouds are displayed. The cloud positions array, it's a state variable, holds position for individual clouds. And in the body, we create clouds using a for loop on this array. Those positions are random positions, which are generated when the view appears. After we start animating the cloud by updating the position of every single cloud. And I'm going to show you, yeah, this is one single cloud. And it basically is drawn using cloud shape. As I said, those are not images. So what I do is I draw 4 different ellipses in 4 different corners. And every single time, the ellipse is slightly different from before. So I've randomized the XY, width and height, a little bit so that it still appears like a cloud and doesn't overlap. But yeah, there is like some complex logic. You can look at the code in the end. But yeah, so right now, it's like a cloud shape. And after I draw that, I'm going to create it in the cloud view, create the shape, fill it with some white color, apply some frame, and blur it. So the blur is what gives the cloud like a nice fluffy and realistic shape. So blur effect is necessary. Right. So now that we've looked at the code, do we have some clue to why it is laggy? If you think about render loop or render phase in particular, it calculates the position of every single cloud. It draws every single cloud shape, and then it's going to apply expensive effects to that every single time, every single render phase, right? So in 16.67 milliseconds or 8.33, depending on the device that you got. So the allocated time for render loop for every frame must be exceeding. And this is how we've managed to really overload the render phase. And the frames have started dropping, making the animation like pretty laggy. And it's not just 1 or 2 frames. If you've only dropped a few frames, like you wouldn't even notice. If you've noticed it, that means like quite a significant number of frames must be dropping. So yeah, let's understand that problem slightly better. Now that we understand the problem slightly better, I'm going to try to fix that. And I'm going to use a magic trick, and it's going to be 1 single line of change to fix this. And I'm sure some of you must have guessed when I said 1 single line. Yeah, I just added the drawing group modifier. So yeah, this is how the change is before and after the drawing group modifier. Some of you may have used this modifier or may have heard about it, but today we're going to try to understand why it works and what it is. So key statement that Apple has used in its documentation to describe this modifier, it's called it basically renders entire group of views as a single image which can improve performance, especially for complex or animated views. So yeah, that's what it says. And after we added the drawing group modifier, what happens is it no longer needs to draw cloud shape in every single phase. It no longer needs to apply any effects to it. It just needs to change its position and render a flattened cloud bitmap image from what it had created before. Of course, it will have to create it once, but basically the animation is where it's moving, so you really don't notice the time when it was created, and then it becomes very smooth. And this is where our knowledge for render loop comes into picture, because we understand why these optimizations really work and what they actually do. So the lag went away, but let's do some performance comparisons. This is the CPU report after about 5 minutes of usage, and comparing it to the previous report, the change is quite substantial. It was more than 100% before, and we reduced it to 33%. And it is important to understand, again, this impacts battery life, so you really want to be mindful of that, so good job to us. And yeah, so I'm sure everyone is now thinking, hey, creating all those images is going to take more memory, so let me open up the suspense. And yes, the memory consumption has changed to 57 MB, which was only 11 MB before. So we are consuming more memory. And this particular case, I feel we've improved CPU usage, made animation smoother. It's an acceptable caveat. And the memory footprint of, let's say, 57 MB is not that bad. But it's very important to highlight that you need to look at these reports before you do any such optimizations. In your case, if your modifier ends up taking too much memory, you may want to avoid it. So yeah, my main purpose of actually building the cloud view was to actually build this animation, especially for this occasion. And I'm going to first try to break it down into different components so that you can understand what's going on. Background is, of course, sky view. The tree and the patch of grass, which looks like land, basically is static image, so nothing interesting. And most interesting bit here are the falling petals from the cherry blossom tree. They basically start somewhere behind the tree, and they're going to end up somewhere at the bottom left of the screen. Both of the starting point and ending point are randomized, so it looks more natural. The animation is also randomized, so it also looks natural. And there is some animation on the petals, if you can see. All of the petals are changing in rotation, so they rotate with the wind. They are drifting in the wind, so if you want to make it look more naturally, they are sort of rotating. There is some opacity that keeps changing so that it gives the effect of the petal coming towards you and away from you. And yeah, there are like some nice effects that are happening on the petal throughout its lifetime. Right, so this view represents a single petal. It's made of petal shape, just like the cloud before. And what we do is we apply a random position to that petal shape. And on top of that, as I talked about, every single petal has some dynamic properties. We apply rotation scale and opacity so that they constantly change. And that's applied every 10 milliseconds. So I start a timer, and then I just basically randomize those different state variables. And this is very important, so let's keep that in mind. Right. This view generates multiple petals using for each loop. And we are going to keep generating those petals using a timer, so the petals continue to fall and we don't run out. So we start with like 5 petals, and then it basically keeps adding petals, and then that gives you the effect of the petals infinitely falling. And yes, so this was how the petals are working. And in the past, with the added drawing group modifier, the clouds really became more performant. And it also enabled us to consume less CPU. So I was like, well, let's do that for petals. So did that. And the effect of adding drawing group modifier is completely opposite to what we thought. Our buttery smooth animation is now hitching quite badly. And that's not just that's just a part of story. We also have very, very bad performance, like from 88% for after about 5 minutes of usage, I believe, it went to 100%, and memory doubled from 73 to 142 MB. And the reason for this is how clouds and petals are very different from each other. Like in case of clouds, we only generate specific number of clouds, and they keep moving around the screen indefinitely, and they are never like regenerated. Petals keep getting created and removed. And the drawing group modifier on the petal view is going to add the overhead to constantly create new bitmaps. Another key difference, as I said, is the dynamic effect. So the bitmaps will need to be recreated to apply that dynamic effect. So it's going to add an additional overhead to recreate those bitmaps whenever rotation, opacity, and scale are changing. So basically, once it creates the bitmap, every 10 milliseconds, it's going to create a new bitmap, which is going to overwhelm the CPU. And it's not worth using the modifier. So the overhead is too much in this case. And based off of that, I really want to share more instances where you should not be using this modifier. As we saw, when the content of views is changing frequently, the benefits may be diminished. And because of the overhead of creating and managing the buffer, it can outweigh the performance gains that you would get. And drawing group modifier should never, ever be used for text views, because text rendering involves a complex layout and glyph management. I'm sure you saw yesterday's talk, there was a lot of detail that I didn't know about. So yeah, watch that. But flattering text into bitmap can lead to accessibility issues and quality loss. So please don't use this on your text views. And applying drawing group to views that require interactivity also can lead to unexpected changes. So from my test, it sometimes works, but well, yeah, sometimes is a big word. So yeah, it may not work every single time. And just to make all of this list easier to remember, most of these drawbacks are actually associated with the fact that drawing group flattens your view hierarchy into a bitmap and is going to cause other problems like effects not seeing properly, like blending. Blending wouldn't work properly if you do like very high like effects like that. Transparency works, so not to worry about that, but like advanced blending may not. And all of your user interactions, if you have complex gestures, like they are not going to work on a view that has drawing group enabled. So yeah, it is best suited for like complex views where benefits of bitmap rendering are going to outweigh the potential downside. All right, let's recap on what we learned today. We now understand how SwiftUI renders things on screen. Well, not completely, but I would like to think at least a bit better than before. We not only learned about some very powerful tools, but now we understand why they actually work. And hopefully we gained a little bit better understanding on what our apps do and why they work slightly better. All right. You can scan the list, this QR code for a list of links. It's got the GitHub link to all the examples that you saw before, some bonus examples that actually implemented, but we didn't get the time to see. So yeah, there was a lot. And I encourage you to like clone the repo, remove drawing groups, see what happens. It's really fun. And I also actually included links to my favorite WWDC videos and some tech talks that Apple did on this topic. So all of that helped me gain better understanding and talk about this topic confidently on the stage. And finally, thank you for listening. I'm beyond thrilled to be attending this conference and still awestruck that they allowed me to speak in front of so many people, and hope to have fun conversations with you all at the booth later. And finally, arigato gozaimasu.